section 3.11 is about something called hyperbolic trig. It does have something to do with hyperbolas, it does have something to do with trig, and those connections are not going to be at all apparent for a while. So you're going to have to hang out until we can see why that's actually an appropriate name. Based on the name, it kind of looks like the sort of thing that a math teacher would invent just to torture her students. So to convince you that that's not the only purpose behind hyperbolic trig, I'm going to actually start with an application, and that's a hanging cable. So if I have two posts and I hang some cable between them, it's going to hang down something like so. I've got a little piece of string here, well, ribbon of some sort. So my arms are being the posts, and you can see this is hanging down like so. That's describing a particular curve. Now, looking at it, it looks like that could be part of a parabola or something like that, but it turns out it doesn't curve quite the same way. The way this curves is like hyperbolic cosine. I pronounce that function y equals cosh x. We just put a sh at the end of the cos that would be cosine, okay? So that's cosh x. It stands for hyperbolic cosine of x. Now, depending on how far apart these posts are and several other factors, this might not be exactly cosh x, but it would be some transformation of it. It might be a vertical stretching or a horizontal stretching or shrinking of things, but it would be some transformation of this function cosh x. Now, what is cosh x? Well, the formula for it is that it's e to the x plus e to the negative x divided by 2. So we build it as the average of two exponential functions. Let me just sketch those. If I have e to the x, now I'm going to just sketch this as a dotted curve, that would be exponential growth. And if I have e to the negative x, that's the reciprocal of e to the x, and that actually looks like exponential decay. So that would look something like so. Cosh is the average of these two things. So I'm basically going to add these two things together and then divide by 2. That's how we calculate an average. Graphically, that means that the graph is going to lie in this middle region, always about halfway in between the two curves. Now, both of the curves have a y-intercept of 0, 1. So cosh is going to pass through that point 0, 1 as well. And I can sort of see how averaging these curves does give me a sort of a U shape. But this formula is very different from x squared, which would give me a parabola. So although they look similar, the curvature of them is going to be very different because they're defined so differently. Okay. So that's our function, cosh x. And one of the applications of it, as I said, is that hanging cables will always hang in such a way that they correspond to a transformation, could be a stretching or a shrinking of this hyperbolic cosine function. All right, so let's just record a few properties of this. Okay. Now we said that cosh of 0 was equal to 1, which means that the y-intercept here is the point 0, 1. Now here we got that sort of graphically. We said both e to the x and e to the negative x actually have a y-intercept at 0, 1. So when I add them together, I'm going to get 1 plus 1. That's 2 divided by 2. I can do that algebraically. E to the 0 is 1. E to the negative 0 is 1. 1 plus 1 is 2 divided by 2 is 1. So cosh of 0 is 1. This graph, it looks like, and it makes some sense based on the application of a hanging cable, that this is an even function. It looks like it's symmetric about the y-axis. So I'm going to say cosh of x is even. Now what that means is that cosh of negative x is exactly the same as cosh of x. Opposite input gives me the same output. I can prove that algebraically, because if I evaluate cosh at negative x, I'm just replacing all of the x's with the opposite of x. So that would be e to the opposite of x plus e. Here I'm replacing x with the opposite of x. But there was already a negative sign in front of it. So my exponent is the opposite of x, all over 2. Notice that's e to the negative x plus e to the x over 2. And when we add, it doesn't matter which of the terms I write first. That's still the sum of an e to the x and an e to the negative x. Okay. So cosh is even. That's kind of neat, because exponential functions really don't have any symmetry to them, but we're able to build this very nicely symmetric function by just averaging these two exponential functions. Pretty cool. Okay. I'll also point out that cosh of x is always bigger than or equal to 1. Notice the graph, it's always positive. We're always above the x-axis, and even more than that, we're always above or equal to this low point, which is at 1. So that's a huge difference with the trig functions, that we don't take on any negative values for this particular function. What I'd like to do is just get a little bit of practice evaluating this function. Now, if I wanted to evaluate cosh at a number like 2, that's not going to be particularly helpful. Let me just put back up here the definition. Whoops. It's e to the x plus e to the negative x divided by 2. I could certainly plug in 2 for those x's, but I'm not going to have a very nice way of simplifying things. But if I evaluate cosh at the natural log of something, let's say I evaluate cosh at the natural log of 3, that's going to simplify pretty nicely. That's going to be e to the natural log of 3 plus e to the negative natural log of 3 all over 2. E to the natural log of 3 is just 3. E to the negative natural log of 3 is not negative 3. Okay. E to any power, I know that's never negative. Here's the graph of e to the x right here. It's never negative. What does a negative in the exponent position mean? It means to take the reciprocal. So this is plus the reciprocal of e to the ln 3, which is 3. So we get 3 plus a third over 2. I'm going to just clear that complex fraction by multiplying by 1 in the form of 3/3. So that's going to become 9 plus 1 over 6. That's 10/6, which I can reduce to 5/3. So numbers in the form of the natural log of something are usually kind of unwieldy to work with when plugging into most functions, but plugging into hyperbolic trig functions, because they're all going to be defined in terms of this natural exponential function, actually is fairly nice. But you will want to make sure that you're practicing that. Okay, and you'll have plenty of time to do that in the homework.